Reading Between the Pixels, Investigating the Barriers to Visualization Literacy. In the current digital age, understanding and interpreting visual data is a critical skill to have. However, viewers may not always fully understand the different visualizations, which can lead to misinterpretations of the underlying data and the story that data has to tell. In this work, we ran a crowdsourced study to understand the barriers people encounter when reading data visualizations. We base our study on the well-known VLAT survey, which tests users' visualization literacy across 12 different charts. In order to really get at participants' mental models for each chart, we augmented the questions in the VLAT to also capture qualitative reasoning from participants. For example, we asked participants to sketch directly on the visualization to show us how they found their answer, as well as to provide written rationale on their thought process. We analyzed the data from our survey through both a quantitative and a qualitative lens. The quantitative analysis revealed which charts participants struggled the most with. For example, stacked charts, whether area bar or 100% stacked bar, were among the 5 charts with the lowest accuracy averages in the study. More well-known chart types, such as line, pie, and choropleths, were among the best performers. For the qualitative analysis, we performed open coding on the 500 incorrect task completions from the study. This gave us a sense of the types of mistakes and hurdles that participants were encountering for each of the chart types. For example, the predominant mistake type for all 3 stacked charts was not understanding the visual encodings used. In this case, the concept of a non-zero baseline for the different data categories. For pie charts, the most common mistake was identifying the correct segment of the pie, but then reading off degrees instead of percentages from the pie wedge. The choropleth, which was the top performer in terms of accuracy, only triggered one type of mistake: misinterpreting the quantized color map and reading off the wrong value or interval. Our analysis of participant rationale when answering a VLAT question incorrectly resulted in a higher-level classification of barriers into 3 main types: translation barriers, encoding barriers, and decoding barriers. We also distinguish between conceptual and operational barriers. Conceptual barriers are those that result from a gap in the viewer's understanding of the task or of the visual encodings used. For example, if the viewer doesn't know the meaning of a term in the task, or if they don't understand how a visual variable maps to the underlying data. Operational barriers, on the other hand, are those that occur when a user misreads the question or the elements in the visualization, such as data values or color legends. Operational barriers can result from a previous conceptual barrier, but they can also happen in isolation as a result of not paying attention. Let's go through the 3 main types of barriers. Translation barriers relate to whether the viewer can understand the question and translate it into a visual query. This can either be misunderstanding the visualization task, such as finding the range of values, or misreading the target of this task. Misunderstanding the task is an example of a conceptual barrier, since it implies the viewer did not understand a term in the question. Misreading the target of the task, on the other hand, is an example of an operational barrier, which can happen, for example, when not paying close attention to the question. Here's an example of a translation error from our survey. In this question, participants were asked to find the range of the data between January 2018 and January 2020. This participant did not understand the concept of range and instead answered the data values for the maximum and minimum dates in the data. The second type of barrier participants encountered are encoding barriers, which capture challenges in understanding how the data is encoded in the visualization. The barriers in this category are all conceptual and can be one of 4 types: misunderstanding the visual encodings, misinterpreting the axis or color map, confounding chart elements with data values, and finally, being unable to estimate a derived value from the chart. The stacked bar and area charts were common targets of encoding barriers. In this example, the question asked participants for the price of peanuts in room service in Seoul. You can see that this participant found the correct city and the bar representing peanuts, but misunderstood the top and bottom boundaries of the bar as representing the range of values for that category. So in this case, peanuts would cost between $35 and $42. Another interesting example of an encoding barrier is when viewers confounded chart elements, such as the range of values in the axis, with data values. In this example, when asked to find the average metro system for this dataset, this viewer concluded the exact center of the chart was the average of the data. The last type of barrier relates to the ability of a viewer to decode a data value from a visualization. This includes reading off the wrong data element, reading the wrong visual channel, or reading off the wrong value for an axis or color map. Decoding barriers are operational, and they can either stem from a prior barrier in translation or encoding, or they can simply happen due to inattention. Here's an example of a decoding barrier from our survey. For time series charts, such as this line chart, several viewers interpreted the line connecting two data points as representing continuous data for that month. This user specifically said there was a lot of change during the month of February, so I took the average. There are two barriers in this example. The first is an encoding misconception of what the axis values mean, and the second is the decoding mistake of reading off the wrong value for the month of February from the y-axis. In addition to exploring the barrier themselves, we also looked into how these barriers affected the time to complete tasks. Our results show that yes, for 10 of the 14 charts, incorrect tasks took longer than correct ones. Charts where the correct task completion took longer included the bar chart, the stacked bar chart 100, the bubble chart, and the stacked bar chart. The average difference in time between correct and incorrect tasks varied by chart, from less than just 2 seconds for the stacked area chart tasks up to over 25 seconds for the bubble chart ones. One notable trend is that for more challenging charts, the time difference between people who got the tasks correct and incorrect tends to be small. That is, participants who got it wrong were only a little bit slower than those who got it right. On the other hand, in simpler charts, the average difference between the two groups tends to be higher. So participants who got the tasks wrong in the simple charts took up to 20 seconds longer than those who got it right. While the absolute number of people who got tasks wrong for simple charts is much smaller, as you can see from the size of the red circles, those who did took much longer to answer. There are a few exceptions to this trend, mostly within the more challenging charts, where the slower participants were those who answered correctly. A particular egregious example of this is the bubble chart, where participants who got the task correct took an average 25 seconds longer. We hypothesized that this is because participants who answered the question correctly took the time to analyze all visual channels and decode the correct one. Ultimately, understanding the pipeline of misconceptions that a user has when extracting information from a visualization is an important step in order for us as visualization designers and educators to be better equipped at closing these gaps. In this work, we contribute a classification of the different barriers in interpreting data visualizations. Thank you for watching our video, and we hope you enjoy the paper.